Okay, so there's a vertical part to this motion, there's a horizontal part to this motion. The guy's flying off the slip and slide, flying through the air, landing in the kiddie pool that he set the right distance away. So what I have to recognize is this, okay, that there are in fact two parts to this motion. Okay, there's a vertical part that I'm going to put in blue, and there's a horizontal part that I'm going to put in black. This is his projected velocity, 20 meters per second, 30 degrees above the horizontal. That has a horizontal component and a vertical component. Would you agree? Okay. Just like any other vector thing we've done in this unit so far. So this side here would represent the horizontal component of that 20 meters per second. In other words, it represents his constant horizontal velocity. Just like in the other projectile motion problems we dealt with, the horizontal velocity does not change. Okay? There's nothing to accelerate the person in the perfect physical world. Okay? There's nothing to slow them down or speed them up horizontally. So how would I calculate V horizontal? Yeah, trigonometry. Same way I did in all my vector addition questions. I find the vector components. This is the x component. Okay, so I'm going to find the x component. It's adjacent to the angle, so I'm going to go cos of 30 degrees times 20 meters per second. That'll tell me how much of that 20 meters per second is directed horizontally. So we got 28.19. Whoop, I did that wrong. Forget that answer. Cos of 30 times 20 times 2. Cos, I am struggling. The struggle is real. 17.3. I probably could have just multiplied that by 10. Anyway, I needed to have that number in my calculator. That's my story, and I'm sticking to it. 17.32 meters per second. Okay, that's how fast he's going to be moving horizontally. That's pretty fast. Okay, that's like Usain Bolt sprinting as fast as he can go fast. I wouldn't want to hit a kiddie pool at that speed. Okay. Now I got to calculate some vertical information because that's all I have horizontally. And what I'm trying to figure out is how far away do I have to put the kiddie pool horizontally from the base of the ramp? So I'm really looking for my horizontally traveled distance. What else do I need to get that? Time, right? I use V equals d over t for the horizontal part of any projectile motion, so I need t. So I better look at my vertical information and see if I can get it from there. Right now, this is what I know vertically. Vertical acceleration due to gravity. And I made it negative. I didn't do that in the other ones. Why did I make it negative here? Yeah, it's going to change direction. He starts going up, he finishes going down, so there's a change in direction. I got to apply a positive and a negative. Positive is up. Okay. All right, here's the other thing I know. This 20 meters per second has a vertical component, but the object's accelerating vertically. So if I calculate this side of the triangle, this is going to tell me my initial vertical velocity. It's going to tell me how fast the person was moving vertically at time 0. After that, it'll be a different number because gravity will be acting on him. Everyone okay with that idea? Okay. How would I calculate that side? Sine of 30 times 20. So, positive 10 meters per second, or 10 meters per second up. Okay. Now, this is some contextual stuff that you don't know yet, so I'm going to tell you it now. When I throw this marker up in the air, how does the speed it leaves my hand at compare to the speed it comes back at? It's hard to see when you're watching it.
Equal.
It's equal. Okay? Remember that whole what goes up must come down thing we talked about the other day? Okay, think about this. Once it leaves my hand, okay, I've given it its initial velocity. It's now accelerating downwards at 9.81 meters per second squared. It'll travel up, going slower and slower and slower until it reaches its maximum height, at which point its velocity will be 0. Okay? That's where it stops, turns around, and starts to fall back down. Now, it falls back down exactly the same distance, at exactly the same rate of acceleration, to exactly the same spot. Well, it's got to be going just as fast when it gets back as when it left. Agreed? Because everything else is equal. Okay? The distance up and the distance down are equal. The acceleration is equal. Okay? One of these ends at 0, the other one starts at 0, and everything else is the same. So the velocity that it comes back down at is the same, provided it's landing at the same altitude it's launched from. Now, we have to simplify this a little bit and just say that yes, in fact, they were the same. Okay? And it kind of looked that way because it looked like the kiddie pool was kind of up on a hill, right? And his launching point was kind of above ground level. So we'll say they were level. Everyone all right with that? Okay. So that means then that VF is negative 10 meters per second. Okay. Do I have enough information to find time now? I do. Okay. Which acceleration formula am I going to use? Right. And with angled projectiles, the formula you use here is going to change all the time. It's all going to depend on what you're given. Okay. So remember when we did the ones where it was projected horizontal, it was always the same acceleration formula. It might not always be the same acceleration formula here. It'll very often be this one, but occasionally it'll be VF squared equals VI squared plus 2AD because you won't know the time. Okay, and you'll have to use like the change in height instead, stuff like that. All right, so we can plug in our numbers here, solving for t. So that'll be negative 10 minus 10 over negative 9.81. So negative 10 minus 10 divided by 9.81. All right, so he's in the air for 2 seconds. That's about right. You probably could have gone 1 Mississippi, 2 Mississippis before he hit the pool. Okay, something like that. He was in the air long enough. It would have been scary. All right, so 2.03 seconds. That's the one number, just like in the other ones, that can go across and be used on both sides of this. It's the only thing they share. So now I can say D equals V times T. 17.32 times 2.03. So if I take those numbers from my calculator, oh, I forgot to not make that negative. Anyway, I forgot to make this negative, so that showed up negative, so it's a typo on my part. But I should place that pool 35 meters from the end of the ramp. Trust my math with your life? I don't either. Okay. Simply because the whole idea of landing in a kiddie pool at that speed is complete garbage. Okay? And you would break your back, if not worse. Because look at the way he landed, right? Like he came in butt first, right? Like he would have had no chance of escaping a spinal injury in a crash like that for sure.
Do you have any theories about how they were able to stop that though?
I do, because I have the Mythbusters episode where they replicated it, and it was actually the next thing I was going to show you.
Oh, sweet.
Busted, right? Yeah, okay, it was CG, but it looked pretty real. It looked pretty impressive, okay? And it looked like somebody could pull it off. And the accuracy part, yeah, as long as you did the calculations, for sure, you could put the kiddie pool where it needed to be The issue would be is the kiddie pool is not enough to save your life. Okay, Adam and Jamie did that into a big lake. Okay, we had plenty of water around them, plenty of depth. Okay, all of that kind of stuff. Landing in that kiddie pool, they would have both had broken backs. Okay, so not really realistic on that. So there's a lot of stuff that we'll look at here in the coming days, like how Hollywood messes up projectile motion. Okay, because I was telling you on the first day that you get we have an innate sense for how things fly through the air, for how gravity works. And when we see something that's weird, we know right away. We just get that feeling that that's not right. Okay, so I'm going to show you another video here, and I want you to see if you can figure out what's wrong about it. Okay.